What about the hybridization of a molecule in which the central atom exceeds the octet rule? What is the shape of the phosphorus pentachloride molecule? Well, the phosphorus has 5 electron regions all bonded, and so this is going to produce a trigonal bipyramidal set of atomic orbitals on phosphorus. To produce this, we need to combine 1d, 1s, and 3p orbitals. A set of 5 effective pairs around an atom always requires a trigonal bipyramidal arrangement and requires the dsp3 hybridization of that atom. Each chlorine can also be looked at and is surrounded by 4 electron pairs, 1 bonded and 3 non-bonded. This requires a tetrahedral arrangement, and each chlorine has 4 sp3 orbitals. If we look at the molecule as a whole, the 5 phosphorus-chlorine sigma bonds are formed by the phosphorus and chlorine sharing electrons, the phosphorus in the dsp3, and the chlorine in the sp3 orbital. The remaining sp3 orbitals on each chlorine are holding the lone pairs. Let's apply our new knowledge to describing the bonding in the triiodine ion. The Lewis structure is shown on the screen. The central atom has 5 pairs of electrons, 2 bonded and 3 non-bonding. Again, with 5 electron regions, we need a trigonal bipyramidal arrangement and a set of dsp3 orbitals. We can also look at the outer iodine atoms, which have 4 pairs of electrons and need a tetrahedral arrangement and sp3 hybridization. So in order to describe this molecule, the central atom is dsp3 hybridized, 3 of those orbitals hold the lone pairs, and the other 2 overlap with the sp3 orbitals of the outer atoms to form sigma bonds. Some molecules have 6 pairs of electrons around the central atom, such as sulfur hexafluoride. This requires an octahedral arrangement of the pairs. In order to achieve this, we need to combine 2d, 1s, and 3p orbitals. This requires an octahedral arrangement of 6 equivalent hybrid orbitals, and 6 electron pairs around an atom always requires d2sp3 hybridization of the atom. So you can see this on the side in the sulfur hexafluoride. The sulfur has its 6 d2sp3 orbitals that it will share electrons with fluorine's sp3 orbitals to form 6 sigma bonds. Another example of this is xenon tetrafluoride. Xenon tetrafluoride has 6 pairs of electrons around the central xenon that are arranged octahedrally, and so we need a set of 6 orbitals to hold these electrons, and so the central atom is d2sp3 hybridized. So this diagram shows the Lewis structure, the shape that is required, and then the hybridization of the central atom. So xenon has the 6 d2sp3 orbitals. 4 of them are sharing electrons with fluorine to produce a sigma bond, and the other 2 are holding those lone pairs. Fluorine, although not pictured, has 3 non-bonded and 1 bonded, so it will be sp3 hybridized. A couple of resources as you start to analyze these molecules on your own. We've been using a problem-solving strategy using this model. First, you should draw the Lewis structure of the molecule, which we have a lot of practice with that. Then determine the VSEPR arrangement, and then finally add this new knowledge of the type of hybrid orbitals required to accommodate those electron pairs. Another resource that I provided in your notes is this table, which includes the number of electron regions, the shape, the arrangement of those electron pairs, and then what type of hybridization is needed, and the bond angle. So it's cut into 2 parts, but you have all the way from 2 electron regions or effective pairs up to 6. Let's look at 3 additional examples before you try this on your own. We're going to look at each of these molecules or ions and predict the hybridization and describe the structure. So we're going to start with, again, another familiar molecule, which is carbon monoxide. It has 10 valence electrons, and this is its Lewis structure. Each atom, the carbon and the oxygen, has 2 effective pairs, so it has the bonding region in the center and then the lone pair on the side. So both atoms are going to be sp hybridized. That triple bond is going to be produced by the sigma bond that is made by the overlap of an sp orbital from each atom, and then the 2 pi bonds that are produced by the extra 2p orbitals for each atom. This may be a little bit more clear if we look at a diagram. Again, the lone pairs are in the other sp orbitals, so you can see 2 sp orbitals. The one in the middle is producing the sigma bond, and then each atom has its lone pair. That produces your linear arrangement. And then if we look at the 2p orbitals that weren't being used in the sigma bond or the lone pair, they are overlapping above and below the molecule to produce those pi bonds for the triple bond. All right, let's look at a second molecule, Bf4- ion. It has 32 valence electrons. The boron atom is going to be surrounded by 4 pairs of electrons, all that are bonded to the fluorine. This requires a tetrahedral arrangement, and we now know that's going to need an sp3 hybridization of the boron atom. We can also look at the fluorine. Each fluorine has 4 electron pairs, 1 bonded, 3 non-bonded, so it is also sp3 hybridized. And so if we look at the molecule, we can see that the boron, the 4 sp3 orbitals are forming a sigma bond with fluorine where they're sharing, and although we can't see them, we know that the fluorine has the 3 additional sp3 orbitals which hold the lone pairs. The final example is xenon difluoride, which has 22 valence electrons. The xenon is surrounded by 5 electron pairs. 2 are bonded, 3 are non-bonding, which again requires the trigonal bipyramidal arrangement. The lone pairs are going to be placed where they are 120 degrees apart, so you can see this kind of triangular shape on the side, and then we can see the atoms across here. To accommodate the 5 pairs of electrons at the vertices of the trigonal bipyramid requires that the xenon atom has a set of 5 dsp3 orbitals. And then again, because each fluorine has 1 bonded and 3 non-bonded electron regions, it is sp3 hybridized. This produces a linear arrangement of the atoms. Again, we can see that the 5 dsp3 orbitals of xenon, these 2 are sharing electrons with the sp3 orbital of fluorine, and then these 3 dsp3s have lone pairs, and again, although we can't see them, the 3 sp3 orbitals of fluorine also hold lone pairs. There are some limitations to this model that we'll address in the second half of the unit. It does incorrectly assume that the electrons are localized, so we do need to add in the idea of resonance structures. This model doesn't really deal effectively with the molecules that have unpaired electrons, and it also doesn't give us any information about bond energies.